What's up? It's Jacob from International Precision Engineering, and I want to talk about application programming for mechanical engineers. What is an application? Well, to me, a script is not an application, even though it can be compiled into an exe, which is a Windows application, or it can take user inputs like as in character inputs or number inputs. To me, like, you're just drifting towards what a real application is at that point. So MS Paint is a real application. You open it or run it and it does some stuff in the background in preparation, but then at some point it just sort of sits idle waiting for you to do something. In this case, pick a tool, pick a color, and draw something. To me, that is an application. These procedural scripts might be part of an application, and they're a good way to test certain components in isolation, but at the end of the day, to me, this is not an application, and I'll be talking more on how to do something like this in relation to mechanical engineering. This might be an example of an application that I might come across. So in this example, we've got a car body that just came off the manufacturing line. We've got a bunch of metrology tools on robots, and what they're going to do is they're going to scan this car and output some human interpretable result. So here the red might mean out of tolerance and green might mean way under tolerance. And what the software application would do in this case would be to take inputs from the user, maybe what type of car or whatever, or maybe this is even controlled by the factory itself, but ultimately the application is going to use hardware to interface with the real world and then use some processing to bring that back into an example of what makes sense to me. Right? I can't look at that body and tell anything from it, but this robot and this software can. Thinking back to when I first started building instruments and selecting hardware components and all this stuff, I was completely lost. I tried to plug it into Python and use that sort of procedural recipe there that when I hit run it would do it, or maybe I could hard code some arguments into it. When I hit run it would sort of act like it's taking input, but I really had no clue how to do it. And then I quickly outgrew things like Python and MATLAB and all that stuff because I really didn't know how to use the library that the camera supplier gave me to, how do I get that into Python? And oh, yeah, I was just really lost. Starting from the beginning, there's a lot of things to consider. So namely, what programming language do I use, or what environment, or where do you even start? What questions do I ask Google to get me going, right? Some considerations when choosing a programming language: obviously skill. Don't try and learn assembly to accomplish a task, right? And we'll kind of go into what that means later, but acquisition of licenses, they're not all free. LabVIEW, if you're a student, you probably get from the university for free, or if you can justify the cost by some of its functionality, that makes sense. Visual Studio is free, or I should say Visual Studio Express is free online. And sort of at the highest level, you hear things like .NET and again, Python and MATLAB. They all have these sort of interface builders and stuff like that. But another thing might be library support. So again, if that piece of hardware you're using only comes with a C++ API, or even worse, like a DLL with a C interface, and we'll talk about what this stuff means, well, you might be sort of strapped into using that, at least to build an intermediate piece to get into a language that you want. So these sort of considerations are the things that are running through my head when I start a project. What pieces do I have? What do I have available? What are my resources? What are my skill levels? What am I trying to do? Obviously, this is a big one: interoperability. We'll touch on that later, but really it just means, can I grab from, say, a SQL server, or can I push to an image file, or can I run this on Windows XP and Windows 10. So we'll touch more on that later, but again, this is a big one, and that's why people love Python really doesn't matter what you're opening it on. It sort of just works, right? Everything's sort of transparent. So again, Python is great in that respect. Once you pick a language, then you need to start like, how do I structure the overall architecture of my program, right? Like here is a conceptual software stack that we'll kind of circle back to, but at the very least, you should segment your code into modules so that it's easier to understand. Things can be reused maybe in other projects. Hopefully there's some examples. If you break the problem down into simple enough terms, there's probably code available online that achieves that particular function. But then there's sort of higher level things or frameworks that are available, or there's information on the web. So again, we talked about procedures, right? Like when I open up a normal MATLAB script, I hit run and it does it, and then it ends at some point when it's done. That's a procedural design pattern. So it does a procedure. It does one specific thing. It's more really just a glorified function. So procedures can be inside of other design patterns too. So for example, object-oriented programming, OOP, is a big one. That's sort of like the next level up, and really all that does is sort of encapsulates code that belong to specific objects or really any abstract container, and we'll come back to that. Things like front-end, back-end, so you could separate code out. Like I want to focus all of my sort of user experience stuff to a guy that really knows that, and then I'm going to do all the low-level hardware interfacing over here, and then somehow we have to bring that together. So let's look at this conceptual software stack here. When I say break things into blocks, like you could take that all the way up to the highest level, one block is my application, and then all the way down to the lowest level, which is like all the individual functions in a program. So somewhere along the way, depending on where, it's kind of like a satellite image too, like your map, you pick the map that sort of fits the area or the region of interest that you're interested in. If you're just looking where is the continent on the globe, well, you're going to have this really zoomed out view, and if I want to know exactly my GPS coordinate of my house, well, I better be zoomed in really close. So this is sort of a really high level thing. This would be like maybe the map of the United States or something like that. But all the way at the bottom would be like hardware. So like that block here deals specifically with controlling the robots, getting data from the scanners, coordinating everything, maybe even like all your cameras, things like that. Over on your left, I have sort of like the human aspect. So I have input devices, keyboard, mouse, joystick, whatever, display, right, computer screen, VR goggles, whatever. And then also I put a data layer there too, because sometimes you save files, take it with you, whatever, open it up on something else. And then you have this sort of intermediate block here. On your right, you have this external API block, and really what that means to me, both the external API and the HMI thing is like on my screen. If you look at sort of like a CNC machine, for example, that dial might directly move the axes to like align something manually or whatever. So I want my HMI to be able to move hardware directly. I also want it to like display finished results. So both ends of these can access any sort of function within my stack. So for example, another computer, if I give it the API, should be able to control my hardware directly, right? So then we talked about hardware. A state controller, I don't want to get into that really, but really it's sort of like an intermediate layer that coordinates between pieces of hardware, for example, or between some database and the hardware, whatever, just coordinates multiple components. So for example, the scanner being on the robot they have to be synchronized so that you can correlate where that data point was that the scanner grabbed relative to your coordinate system. So all that stuff has to be synchronized. That would be sort of maybe loosely called a state controller. Then you have all this data and you need to do something with it. So maybe the machine sits there and thinks for a while, right? So you have this processing engine that sort of handles that. And then once it's done, the computer's in ones and zeros and you need to get that to the display. So maybe it compiles images, even though you're saving in raw measurement format. I need to show the user, do a measurement report, whatever. So there's sort of that thing. So you can see here, like, the lowest level programming would be interfacing with hardware, and then the highest level programming would be like, show me on the screen. And then in my HMI controller is like, when I, like a CAD model, when I click and sort of scroll around, this thing's gonna do something in 3D space. So all that would be an example of really high level programming. And then low level would be specifically connect to this piece of hardware using this code or whatever, this serial number. That's all low level functions. So we said we have to pick a programming language or understand which language is good for what. I think actually a historical perspective helped me understand, like, where do I want to be in this spectrum, right? You hear names like assembly, C, C#, C++, Python, or maybe even like HTML as a programming language, right? So I think that if you do yourself justice, if you go back and sort of like do a quick wiki search of the history of these programming languages. So like time-wise, from 1950, assembly came around, and then on the top, this is what a computer looked like in 1950, okay? So obviously they're not talking about graphics. So assembly language is really squeezing every bit of performance out of your machine to accomplish the task as fast as possible. So somewhere along the way, 20 years later, they're like, we need to build something that's easier to read and write, and maybe we could build some higher level function, and then we'll compile it back into assembly code, right? So that's where C came from. And then this is really what a computer looked like 20 years later. So it's something that could fit on your desk. It's a lot more capable. Well, maybe we don't need to worry about every clock tick, but we still want performance. So again, console programs, simple spreadsheets, database, all that stuff, you know, your input or output to this thing is like characters on the screen, right? So again, there's no graphics, but it's really, again, the machine's not very capable, so we need to squeeze every bit of performance. Memory is really crucial, so there's a lot of memory functions in C. Then maybe about 10 years later, someone said, well, this is ridiculous. Computers are a little bit more capable now, and I don't really need to be so concerned about memory because we're getting more of it. And but I still need to think about it. So C++ came along, and then it's more into like encapsulating code with classes and all sorts of extra things that provide more programming efficiency at the cost of not maybe processing as efficiently as it could. But again, no graphics, right? Hey, we have a floppy drive now, so maybe we're not so concerned about file size and all that stuff, but still, what was a floppy? Like one of these 8-inch floppies, I don't know. Like, I remember the 3.5 was 1.1 megabytes, so probably a couple kilobytes, maybe a couple hundred kilobytes. Fast forward to 20 years later, the landscape was a lot different. So now we have things like Windows 95, and we're starting to get away from console applications, and we're going to like Windows now, where I drag and drop folders, and I'm back to thinking more like I have a better representation of the world because I have a folder and a desktop when that's what I'm used to when I'm at work. So right around that time, there was a bunch of languages that spawned, and it was really all about how do we handle graphics and front ends and user interaction and games. And so it's sort of a paradigm shift, and no wonder why C# really is great at handling that, because that's really about the time that it came out. another thing you'll notice is like, look at the skill level in the programmer. You came from somebody that's their job, or you're not touching it, all the way to here's some kid playing on this thing a game, right? So also around this time period with languages like C#, they start restricting access to things like memory, and they're like, well, don't worry about it, we'll handle it for you. And in one aspect, hey, that's great. In another, when you're trying to get performance, there's a big overhead here. And that's why, like, no matter what era you're in, the computer always takes like 2 or 3 minutes to boot because they're less and less worried about efficiency and all that stuff, because they're sort of like assuming more and more and more and reusing more and more bigger blocks. And there's a lot more garbage overhead that's happening in here, but the applications can be developed much, much faster. So that's the sort of, to me, the end of where like programming efficiency came out, until right about that same time, it's like the PIC came out, the microcontroller, and like anybody could get their hands on one. It started out expensive, and then the price sort of slid down, and when I was a kid, so in late 90s, these things were $1. Right? So, I mean, anybody could do that, but the programmer was like $100. So there was a little bit of an investment, but I could put one of these chips in everything, a plant, whatever. And then that's where like the open source thing just exploded to me. So another perspective to look at this is like, well, did we throw all this stuff in the garbage? Like, do we ever still use assembly code? Like, I think I just said like, don't worry about assembly. It's like, no, don't bother with it. But it depends on what you're doing. So you can also look at this as like, well, what were these languages designed for? So like the Arduino, man, I could go online and like, what do I want to do with an Arduino? And like somebody posted a whole project and like, buy this, punch this code in, and run, right? Like, and it's all out there for anybody to use. But really sort of has its limitations. It comes back to me, right? Like, well, I got to buy that piece of hardware because I don't really know how to plug it into whatever he did. I don't really understand programming. So coming back, you start saying like, oh, well then if I'm going to get into it, I'm going to use the sort of the most current and high level language. And that would be something like C# or maybe like a Java or something like that, scripting language. Or even Python, but really all of that stuff is tailored again towards like graphics. So if you need like a really smooth UI and all that stuff, like that's where these components are going to be made for. So coming back to the hardware world, so here I see almost all of the hardware that I get has a C++ API. And to me, that's like a sweet spot of like, there's a lot of power there, and then there's also a lot of tools there that keep efficiency high and give me and enable the control that I want. Like you go into C# and you have to like tell it, hey, I'm gonna use an unsafe block to access pointers, right? Like, and if I'm doing imaging or image processing, it's all about pointers. I don't want to copy memory, so really, like C++ is kind of a sweet spot for me, and we'll see later that that's sort of where I fall. But, well, do we ever still use C? Well, if you were going to fire a missile off, I think you'd be pretty concerned about something crashing. So you really want to have a good eye on your code, or maybe like an ATM. It has to work. It has to work. So critical systems definitely still use C. And then down at the embedded level, so I heard through the grapevine that Ford, so this would have been about 3-4 years ago, put their entire radar-based road mapping system, again, starting to drive towards that autonomous thing, or I think the auto braking's out now, or if you get too close, the car will slam on its brakes automatically. That whole system, that radar-based system, actually generates sort of like a 3D map of where it's going and all that stuff. So it's processing an enormous amount of data, and they had to put it all on like a $5 processor. So I guarantee you that somebody was taking somebody's high-level code and taking clock ticks, shaving clock ticks off, at the embedded level. And whether that was whether or not that was in assembly, I don't know, but I bet you that they're definitely in this low area to do that kind of processing on that cheap of a processor. So let's look at a really successful example of a piece of software. For example, Instagram on a smartphone. What is that doing? Like how are they getting you the information that you want so efficiently or whatever, right? So from my understanding, the only thing that your smartphone is doing is interpreting gestures, right? So I touch here, I swipe, I whatever. So it interprets your gestures, sends all that information through the internet to the Facebook server or Instagram server, whatever, where they're running a lot of code, and there they decide what your history is, who your contacts are, all that sort of complicated algorithm stuff, what you like, what you don't like, what's going to keep you engaged so that they can make advertising revenue. And then they generate sort of a picture in terms of like an HTML script, pipe that back through the web, reconstruct all of that using the software on your phone. Again, that would be the browser on your phone, Safari or Chrome or whatever, and then the phone software shows that to the screen. So here's an example of where, like, this is a perfect example of how we're sort of tending back towards the original computer model where you have a terminal and then a server somewhere else doing the heavy lifting. So the only thing your phone is doing is interpreting gestures, sending the information out, reconstructing the image or the information that it gets back, and then displaying it to the screen. So I think that's why processing, and again, I'm not a computer engineer, but I think that's why even crappy phones still work good, because they're not doing anything. They're just interpreting your gestures, and then maybe like a brand new, fresh, clean phone might scroll that much smoother, right? Like have that acceleration and deacceleration, or the refresh rate is really high. But at the end of the day, it's not doing any processing. It's not mining for information and filtering. That's all happening in the server. So let's take that back. Let's take that successful example and bring that back into our software stack. So with this understanding that, well, all the high-level UI stuff, well, that's going to be real great in C# or maybe one of the other .NET languages, or maybe even like LabVIEW or something like that. There's a lot of UI power in those high-level languages, but remember, I'm dealing with cameras and raw hardware and stuff like that, so I want to be in sort of C++ land. Well, I could chop this thing in half. I can bring over my external API and say, well, if I expose all the APIs through this external API and then call them from my sort of, I'll call it C# UI, I'll have my UI interpret my gestures, and then what am I intending to do? And then I tell C++, this is specifically what I want, and then there's a known return, so sort of like a handshake there, and then it shows my result to the screen when it's ready. So I'm going to chop this thing in half and use high-level language to do my gestures just like Instagram would, and then all this sort of heavy processing stuff I'm going to do in C++ somewhere else. Really on the same machine in my application, but it doesn't have to be. You have to start somewhere, and for me, that was, can I get these individual pieces of hardware to work, right? Remember, that was my limitation. I'd get this camera that had a C++ API. How do I get that into the computer? And then once I was successful at that, like what do I do with this? So I can command it to snap a picture, and I can set the integration time, and I can do whatever. But then what? How do I get my clicking on the screen, or how do I even show that image to a screen? You know, all that sort of came later. So I absolutely had to master this hardware block first. So let's look at that. In this simple example of, let's take a microscope. Okay, so here in this simple thing, I have my hardware module isolated by these generic interfaces, again, kind of like me sending the gestures to the Instagram thing over the internet, like that doesn't matter what phone I have or what system is running that Instagram application. The information that gets sent is always the same. So I call that like a generic interface, right? So it doesn't matter if I use an Android today or an Apple tomorrow. There's something in there that can handle the translation of gestures from the Apple information or the Android information back to that common interface, and then it sends that information. So there's like a translation piece, right? So let's look at how the hardware might go from specifically to like one specific piece of hardware to a generic interface, and how would I do that? In this example, I'm going to use a XY stage from Aerotech, and then I'm going to use a Z stage from Thor Labs, or a motion stage that I'm going to call my Z, and I got it from Thor Labs. So I can't just like plug these things into the same controller, right? So there's going to be some interaction there. Then I've got like some camera generally, or optical stack or whatever. So some like maybe a bunch of components that comprises a camera, or it could be simple as just an imaging device or an imaging chip. I'll have a lighting controller, so I'll like drive somewhere, optimize the illumination, snap the image, right? And maybe I'll do that several times. Here is like inside the hardware block, I have at the very lowest level, I have X, Y axes, a Z axis, a camera, a light. So I have 4 pieces of hardware that I need to somehow like jam into a common interface. Maybe my X, Y, and Z all fall into some like system motion controller, right? So here I might be able to have like an instrument layer that says, hey, move to position XYZ. That translate, oh, well, I need to send my XY to that piece of hardware and my Z to that piece of hardware, and then sort of like query that back, are you there, are you there, and like handle all that so my instrument doesn't care about any of that stuff. So I have these, again, generic interfaces, so maybe my XY axis and Z axis, even though they're separate pieces that have very specific API calls and libraries and all that stuff, I'm going to handle all that inside of each one of these blocks and then push it to, again, some generic interface. Like, what's generic about motion? Well, move, enable, e-stop, stuff like that. So these should have almost the same API. Maybe this one's a little different because it's 2 axes instead of 1, but ultimately the functionality should be the same. Same thing with sort of like, if I look at an instrument, it has motion and a microscope on it, but in my microscope I have a camera and a light source, right? So I can sort of like, well, I could split that out. And this is a really good example. So if I have this generic interface and I want to change my light controller, all those changes are isolated to that. If I were to start pushing low-level calls up into like higher level points in the program, it's going to be a really nightmare to change any piece of any specific component. So again, it might seem redundant that I have all these sort of like extra layers, but at the end of the day, it's like it helps you segment everything. And also, if I know that there's a problem with that light, well, I'm going to start to look there, right? And I'm going to sort of test just this little block, maybe in a separate program or something, and I know that none of this is going to influence that. So if this works and there's a problem up here, like, well, maybe I'll sort of start working through. So it really helps troubleshooting. It really helps, it enables you to test in isolated blocks. It enables you to switch out hardware without too much pain. Again, assuming that you have some foresight into what that generic interface might be. So how do I handle that in terms of an architecture? So one simple way to do it, and again, this comes back to like what capabilities does the team have? So I'm already sort of like, well, I'm making you learn programming in general and libraries and all that, and we're not using a simple language like Python, or maybe we are in this case, but here I'm going to use the object-oriented model in C++. So on the far left, I have sort of the lowest level, and then it starts shooting up that pyramid going to the right, which puts it back to the highest level. So here, I've got a class for each one of those boxes, and you could have it be a DLL or a separate DLL, like whatever interface you want. The class is nice because it, when you use IntelliSense, for example, in Visual Studio, you start typing the name of the object and it lists all the functions and only the functions related to that object. So in terms of like programming efficiency, to me, this is what works for me. I don't know, might not be the best. So again, yell if you know of a better way. And with an example, right? Because somebody's like, oh, use the view model view approach. And I'm like, okay, let me Google that. And it like made no sense to me at all. So here is an example that I hope you could see its simplicity and its capability in this example. I've got two classes that I have to define, one specifically for my Thorlabs motion system and one specifically for my Aerotech motion system, right? But again, look at sort of the functions that are exposed in each one of these classes. So stop, enable, move, right? They're the same. The differences might be from Aerotech, I have my move as an array of doubles because it has an XY, or I could do double double or whatever, versus my Thorlabs motion is really only designed to do one axis at a time. So, but again, and then in each one of these specific classes is going to be, how do I connect specifically to that piece of hardware? How do I translate the generic move command into a very specific thing that might be like move linear or move absolute, or like set up some profile, and then, or is it asynchronous or synchronous? Like all that stuff happens behind the scenes of this, right? So you're reducing your visibility of the higher level function to these generic things, and then you can set all that up internally in there. So here's sort of like, you could say, a redundant layer with the system motion one, right? So in the system motion class, my objects now are the Thorlabs motion object that I'm going to call MZ-axis, and out of convention, a member of a class, I just do M underscore to say that that's a member variable or a member. So I have a Thorlabs motion object, I have an Aerotech motion object, and then I named them. And then in there I expose, right, my int move, or my move function that returns an integer, might be an error code or whatever, but generic move. But in here I have an array of positions, but it would be 3, right, X, Y, Z. And then inside that move function, it knows that, well, I need to send X and Y to the Aerotech and then my Z to the Thorlabs. So again, all that sort of processing and all that stuff is behind here, and I'm only exposing simple functions. Same thing with stop and enable all, right? Like all that knowledge of what's underneath happens inside of this class, or inside the each of these functions. And then you could say that again, well, my instrument class would be the next higher level or in the hierarchy, right? And I say my only function here, because it's a simple example, is like measure, do it. And then I'm going to hand you a list of locations where I want you to do it, right? Or I guess that could be a double pointer, it could be a 2D array. But basically go and do it. Do what I tell you to do, and all that low-level stuff might be in here. So now if I have multiple instruments on a robot, right? So if you look at some of those pictures, they might have a camera and a scanner or a touch probe or whatever. You can have multiple instruments on that robot, and it might know how to measure given some position or whatever, right? So this is what I mean about modularity, and this object-oriented approach really works for me. Next time, I'll talk about more specifically how do I break this up into my front end and back end. And in there, we'll talk about Win32 DLLs. That's the method that I chose because it's a generic C interface. It's sort of like the lowest level thing you could do. I don't use Visual C++ because, again, that gets me sort of too higher level and I can't access pointers and there's all sorts of restrictions. So I'm using unmanaged C++ in Win32 DLL on the back end and something like C# on the front end. So we'll talk specifically how I do that. And then that comes back to the interoperability thing. Like .NET's really good at using on multiple systems, it doesn't matter, but then my libraries and all that stuff have to work and have to be specifically targeted. So it brings up that deployment and interoperability concern too. Please comment if you think this is useful, if you need more elaboration. Generally nobody watches these for a long time, but the reason I do these longer videos is because I get specific comments and I get a lot more genuine interaction, a lot more like deep interest in things, even though nobody watches the video. Not nobody, but fewer people watch these videos. Don't be afraid, email me, message me, ask me a question in the comments. The more you put in the comment section, the more it might help somebody else, so don't be afraid to fill it up. And thank you, see you next time.